Hello and welcome to All Maths Considered. Today we want to look at a problem from the St Petersburg Mathematical Olympiad from 1994. The problem says, given positive integers a, b, and n, where n is at least 2, assume that a times b divides a plus b to the nth power. We need to show that b must divide a to the power n minus 1. If you are interested in trying to solve this problem by yourself, hit the pause now. In a moment I will give some hints and background to the problem. After this, I will proceed with the solution. Okay, let us now proceed with the hint for this problem. And the hint is to use a fundamental theorem of arithmetic, also known as the prime factorization theorem. Recall that the theorem says that for every positive integer n, we can uniquely write it as a product of prime powers. So formally speaking, any integer, positive integer n can be written as a product p1 to the power of alpha 1 and so on, pk to the power of alpha k, where p1 is less and so on less than pk. These are prime numbers, and alpha I are positive integers. Before we proceed with the actual solution of the problem, let us develop some background information using this theorem. So it's most useful when we are looking at the questions of division between numbers. So let us develop some background. X being a positive integer and p a prime number. Then we will introduce a number c of xp. Let it be the maximal exponent dividing, in other words, x can be written as p to cxp times x tilde, where p does not divide x tilde. So we can say that c of xp is maximal number of times as a prime p divides x. This has following properties. First, if x divides y, then c of xp is less or equal than c of yp. This is true for any prime p, for all p. And this makes sense, right? Because if x divides y, then the number of times the prime p divides x cannot be larger than the number of times p divides y. 2, we have a formula for c of xy p for the product. This is simply the sum of the exponents. This makes sense. And finally, if c of xp is strictly less than c of yp, then we can also say that c of xyp is equal to c of xp. This is because when we are dividing x plus y by the prime p, we can first do it c of xp times, so this will work both on x and on y, after which the first summand will be not divisible by p, while the second summand will still be divisible by p, since c of yp is larger than c of xp. So c of x plus yp is equal exactly to c of xp. Finally, before we proceed, let us note that we can strengthen the first property a little bit and make this equivalent. That is, we can also go backwards. If c of xp is less or equal than c of yp for all primes p, then we can also conclude that x divides y. This is an important property which we'll use later. If you now want to try to solve this problem using the hint and the background information which we have given, hit the pause now, or else just wait and we'll proceed with the solution. Okay, let us now proceed with the solution. So I have formulated here the problem again, just so that we recall. So we have that AB divides a plus b to the power of n. We know that n is at least 2, and we need to show that b divides a to the power of n minus 1. First, let us interpret this condition ab divides a plus b to the power of n. So by the binomial theorem, a plus b to the power of n is equal to an plus bn plus number of terms, each of which is divisible by ab. So ab divides a plus b to the power of n is the same as to say that ab divides a to the n plus b to the n. Furthermore, let us assume that the conclusion of the problem does not hold. So let us assume that b does not divide an minus 1. In that case, there exists a prime p such that c of bp is strictly larger than c of an minus 1 p. So let us say that alpha is equal to c of ap and beta is equal to c of bp. Then what this says here is that beta is larger. Now c of a to the power of n minus 1 p is the same as n minus 1 times alpha. So first of all, this is of course larger or equals than alpha, since n is at least 2. And second, we can also rewrite this to say that beta plus alpha is larger than n alpha. Let us go back to the condition that ab divides a to the n plus b to the n. We know that this means that c of abp is less or equal than c of a to the n plus b to the n p. We know that this is equal to alpha plus beta, c of ap plus c of bp. Here we know that c of a to the np is less than c of b to the np, because beta is larger than alpha. So therefore we know that this is equal to c of a to the np, which is n alpha. This gives us a contradiction, because here we have alpha plus beta less or equal than n alpha, and we know from before that alpha plus beta is larger than n alpha, thus completing the solution of this problem.